For this presentation, I'm going to be talking about passive solar building design and building integrated photovoltaics. Both have the potential to turn buildings into their very own energy-efficient power stations. Combining both of these ideas meets the goal of energy-efficient design and sustainable energy generation. Passive solar building design aims to harness the sun's energy for the direct heating or cooling of living spaces by exposure to the sun. Design elements, the placement, and building materials can decide what happens when the sun strikes the building. It can either reflect, transmit, or absorb solar radiation, just depends on what your goals are. Passive systems don't involve heavy use of mechanical or electrical devices like air conditioning to move that solar energy throughout the house or building. Building integrated photovoltaics, or BIPV, on the other hand, replaces the outer layer of a structure with the PV materials. Typically, BIPVs are integrated during initial construction rather than retrofitting or mounting them to an existing building, such as traditional solar panels. This will save on building materials and electricity costs. It provides zero emitting energy source for on-site use or exporting to the grid, and it has great architectural and aesthetic appeal. The basics of passive design are very simple. There are 5 elements. The first is the collector, which is the large glass area or window facing south, which allows the sun to penetrate the building. It should not be shaded, at least during the heating season, to allow as much heat to enter the building to prevent the need for electrical heating. The second is the absorber, which is typically the floor should be a hard, darkened surface that sits in the direct path of the sunlight and that absorbs the solar heat. Third is the thermal mass, which sits below the absorber that can retain and store that heat. Fourth is the various methods of distribution to carry that air throughout the house or the solar energy throughout the house. And 5 is the control. During the summer, you don't want overheating, so they typically have an overhang over that window to shade the summer sun, which sits higher in the sky, to prevent too much sun from directly entering the building. I wanted to focus on passive cooling since it's more relevant to Phoenix. There are 2 elements to passively cooling a building. Number 1 is reducing the heat gain. This can be done through insulation within the building. In a place like Arizona, warm and dry heat, the most efficient insulation is going to be within the rooftop or the attic. Another is air tightness. You're going to want to prevent additional heat from penetrating the building through tiny cracks. Shading is also extremely important. So planting additional vegetation to shade the walls, the roof, the windows, or being in close proximity to other buildings can also provide shade. If that's not enough, you can double glaze the windows, so any sunlight that hits the windows, double glazing will reduce the amount that actually enters the building. Other unconventional but very popular emerging techniques would be a green rooftop. So in that bottom picture is an example of an Arizona green rooftop where they used prickly pear cactus. That's going to act as insulation as well as shading. It's a native, durable plant, so it's going to be low maintenance. And another is cool rooftops. So painting your roof a lighter color, such as painting it white, can do the trick. Or this example in the top left is a picture of an aluminum rooftop, which has a very high albedo. It's going to reflect a lot of that solar energy, prevent it from absorbing into the building, and underneath it's going to allow for airflow, so it allows more heat to escape. Which brings us to the next component, which is increasing the heat loss, allowing that trapped heat that's inside the house to escape. You can do this through maximizing cool breezes, so in areas that do have a lot of breezes naturally, you can create air chambers through strategic planting of vegetation, allowing that wind to funnel through the house basically. If that's not feasible, you can use the idea of convection, which relies on the fact that warm air floats and cool air falls. So you're going to want high level ventilation near the top of the ceiling to allow that warm air that floats to the top to escape. Another is earth coupling, basically having a large concrete slab as your foundation for the house, which can act as a heat sink because it's relying on the lower temperature of the soil. You'll likely need additional cooling methods. So as you can see, a window design is very important. Traditional sliding windows that you see in a lot of homes in Arizona actually only allow for 50% breeze to enter. A casement window is actually the best design to allow the greatest amount of airflow. Ceiling fans can surprisingly reduce your energy consumption by 75%. They're very good at circulating air around people, making them more comfortable and the air conditioner to work less hard. But yes, in Phoenix, you're also going to need some sort of air conditioning. That is where hybrid cooling systems can come in. It's kind of like a smart air conditioner that can combine the passive cooling of your house with the air conditioner and use both in combination for the most efficient and effective way of cooling using the least energy. The only downfall to this is that it requires an early decision in the design stage, so it's not very effective if you add it on at a later time. Now moving on to building integrated photovoltaics. There are three main applications. One is the facade. So this is where PV is integrated into the sides of buildings vertically, often replacing glass with a thin film solar panel. Another is rooftop. So this is PV material that completely replaces the rooftop itself. Sometimes the whole rooftop, sometimes part of it. It could either be a single large glass solar rooftop, or it can be mini solar shingles that are mounted in place of regular roof shingles. And lastly, glazing, which is almost like painting on ultra thin solar cells onto a glass. So that's going to tint the glass, allowing the daylight to penetrate while also generating electricity. This is often used in skylights or greenhouses currently. Although BIPVs make use of various new technologies, the basics of PV solar is the same. They're composed of semiconductor material, which when exposed to light, absorbs the light's energy, transfers it into electrons. This extra energy allows electrons to flow through the material as an electrical current. This current is extracted and it can be used to power a building. Efficiency of a PV cell refers to the amount of electrical power coming out of the cell compared to the energy from the light shining on it. This indicates how effective the cell is at converting that energy from one form to the other. The band gap is another important term. It indicates the wavelengths of the light in which the material can absorb and convert to energy. When it comes to building integrated photovoltaics, they often use thin film cells. They're easy and fast to manufacture, and they're made of three main parts. The first is the semiconducting material, known as the photovoltaic material. Second, it has the conductive sheet. And third, a protective layer, which is a thin layer of either high-quality glass or plastic to improve the durability and lifespan. The three most popular types: cadmium telluride, which is very efficient, but cadmium is toxic, so that is a current downside. Another is amorphous silicone. It is more durable, it's less toxic, but it's also a bit less efficient than the cadmium. And then another is the copper. It has the best efficiency potential, but they haven't yet figured out a way to transfer that potential outside of the lab. So probably the biggest appeal of building integrated solar is transparent solar panels or photovoltaic glass. so their ability to be used as windows or the glass facades of buildings. There are several different types. You can have partially transparent, which can serve two purposes. It tints the window, reducing the solar heat from entering the building, while simultaneously producing energy. This type, the efficiency is at around 7 to 10%, which compared to traditional solar panels of over 20% efficiency is still pretty low. Fully transparent PVs also have a lower efficiency. This is even newer technology, but it has a higher surface potential. This is because they can be used on all sides of the building to capture as much sunlight as possible. They don't need to be at optimal tilting range, so this makes them ideal to be used for vertical building facades. They look great, but another downside is that they degrade quicker. So one of the newest technologies I wanted to highlight was perovskite solar cells. This is a group of hybrid organic, inorganic PV materials connected to atoms of tin or lead. And this is important because this type is very fast approaching the efficiency of silicon. They're cheaper, easier to make than silicone. They have the translucent capabilities. They have a tunable band gap for ideal solar energy generation. And like I said previously, the band gap is an important element for efficiency. Also, production requires 20% less materials, and they don't use rare earth materials, and the manufacturing process is also less energy intensive. Now, there are many disadvantages and challenges currently since it is so new. One of them is that the material is very unstable in nature, and the natural elements of air, wind, sun, rain, they break down the material even quicker. Also, the best perovskites contain lead, which is very toxic. It's a neurotoxin. So if they were to be damaged, you're going to risk exposing people and the environment to lead. Another downside is that they are just simply not ready for commercial use, but they are being tested, including on a building in Phoenix. So the advantages for targeting energy efficiency in buildings and building integrated energy generation in particular are that buildings and the construction sector add up to 1/3 of total energy consumption in the world. That represents 40% of carbon emissions into the atmosphere. Using passive solar design, energy efficiency of buildings could improve by 25% or more. Harnessing the power of the sun's energy through buildings and glass windows themselves, that can yield a huge energy potential of all new buildings constructed going forward. With advancements, there may also be easier ways to retrofit older buildings with BIPVs. These are not without disadvantage. For passive solar design in particular, you're going to have higher upfront costs when constructing a new building. About 10% higher is what the estimate is. Also, it is very difficult to add passive solar design aspects to an existing building, so it's mainly just for new buildings, whereas older buildings are going to need to find other ways to be more efficient. For BIPVs, disadvantages are also the higher cost, but this is because it's a newer technology. It is expected to decrease as the technology matures. Another disadvantage, the thin film currently has a lower efficiency. Again, it's possible for that to increase as technology gets more advanced. And again, it is difficult and expensive to retrofit onto older buildings, so this idea is also best when considering new building construction. I wanted to end with an example of a building that successfully combined passive solar design with BIPV. So this is the FKI Tower in Korea. It's a 50-story high-rise in which by angling the wall panels on the outside of the building 30 degrees for the sun, the amount of energy collected from the building integrated photovoltaics were maximized. And then, because of the wall panels that are angled toward the ground 15 degrees, they minimized the amount of direct sunlight that entered through the building. So that reduces overheating as well, while still allowing a lot of natural sunlight into the building. The bottom right is a picture of the expansive rooftop atrium garden with custom solar PVs at the angle, ideal to minimize casting shadows on each other and the garden below. The materials used in the building are durable to ensure a long lifespan and uses low energy LED lighting. The building is currently the most sustainable tower in Korea, made possible through the building integrated photovoltaic system and the building's exterior wall and roof. Also, an underfloor airflow system, ventilation, and energy efficiency while reducing lifestyle cost. The building also features an advanced building integrated geothermal system, which saves the tower another 10% energy savings. The tower can generate enough energy to power 274 households for an entire year and will reduce carbon emissions by 394 tons per year. The result is a 25% energy use reduction for the building and a 31% cost savings. So this could be the future of all new building construction, and I'm really excited by it. I want to thank you guys for listening to my presentation, and if you're interested in learning more about these ideas, you can check out my citations and visit the websites where I found all the information. Thank you again.